In this discussion video, we will do an epsilon delta proof for a close to linear function. So we have this piecewise function, one of the pieces is linear, and part A asks, what is the limit as x approaches -1 of this? And this practice problem is not from one of our worksheets because I want to leave the worksheet epsilon delta proofs as a source of practice for you. So I want to begin by giving you 1 minute to try part A here. 4, 3, 2, 1, pause it and try part A for a minute. Alrighty, so hopefully you did that. Hopefully you paused it and tried part A for a minute. Let's begin by drawing a picture just so we can visualize this function and this limit. So I'm going to label -1 on the x-axis, and at -1 the y value is 6. So I'll have a point here at -1 comma 6, and everywhere else it has the shape of this line, -4x plus 5. So the y-intercept of that is 5, and then it slopes downward, has a slope of -4. So it looks something like this, and then it skips the x value of -1, and then it continues on upwards. So our graph has this sort of shape, and we want to know as x approaches -1, what is that limit? So that depends on, well, where is this hole? There's a hole at -1 comma something. And to figure out that something, I could do this limit. When it says x is approaching -1, that means x is close to -1. But when we talk about a limit, it's not allowed to be equal to that number, but it's not equal to -1. Okay, so our limit, we'll get the limit as x approaches -1. And when x does not equal -1, that's the top piece of this piecewise function, -4x plus 5. And now let's just plug in -4 times -1 plus 5, and that equals 9. And that's our limit. So that is going to be the y-coordinate of this hole, 9. All right, part B now says, well, prove this using epsilon delta. So do an epsilon delta proof. So I want to give you 7 minutes to try this one on your own first. 4, 3, 2, 1, pause it. Pause it for 7 minutes to try this. This is going to be really good practice doing one of these epsilon delta proofs, which is especially important because this is one of the more conceptual sections in our class. All right, so we begin these with scratch work. So begin with scratch work. And the idea with scratch work is we work backwards to guess a value for delta. So remember that if we look at our epsilon delta definition, our goal is to find a number delta such that when the distance from x to a is in between, strictly between 0 and delta, then the distance of f of x, our y values, from L will be less than epsilon. In other words, it'll guarantee that I'm in the epsilon window. So we're trying to find a delta that works in a sense. So what I'm going to do is work backwards. I'm going to say, let's let the absolute value of f of x minus L be less than epsilon. All right, so returning to our scratch work, I usually get it started by writing kind of the overall statement. So I'm going to let epsilon be greater than 0, and what is it that we're trying to do? We want to find a delta that's greater than 0 such that s dot t dot such that if 0 is less than the absolute value of x minus, what was our a? A was -1. So I'll have x minus -1 is less than delta. So this will become absolute value of x plus 1. If that's the case, then the absolute value of f of x minus L, and based off of our picture L, the limit is 9, should be less than epsilon. And in our scratch work, instead of trying to find this delta first, we are going to start with what we're trying to get. We're going to start with this inequality being less than epsilon and work backwards. All right, so let's write the absolute value of f of x minus 9 is less than epsilon. So what does f of x equal? Remember, it's a piecewise function. But the fact that 0 is less than absolute value of x plus 1 will mean that x is not allowed to be equal to negative 1. And if I look at my piecewise function, when x is not negative 1, my function is negative 4x plus 5. Okay, so the fact that x is not negative 1 means f of x is negative 4x plus 5. It's the top piece. So f of x is negative 4x plus 5. And then we have that minus 9. This is less than epsilon. If I simplify this thing in the absolute value, we'll get negative 4x minus 4. Okay, and remember, my goal when we start with this is to try to make it look more like this delta absolute value inequality. So I need to get this x plus 1 in the absolute value. I can make that happen if I factor out a negative 4. It leaves me with x plus 1 in absolute value less than epsilon. Now let's split this up into the absolute value of negative 4 times absolute value of x plus 1 is less than epsilon. I know the absolute value of negative 4 equals 4. So let's divide that, and we'll get absolute value of x plus 1 is less than epsilon over 4. And now this matches the first part with delta. Absolute value of x plus 1 is less than some stuff. This is the stuff. I'm going to let this be our delta. Okay, so the purpose of the scratch work is to get a guess for delta. Now we have it. Now we're ready to write the proof. So I'll put a line here. We are ready for the proof. And our proofs always kind of begin with the same first sentence. I write something like, given epsilon is greater than 0, then I say what I'm going to pick for delta. We are going to pick epsilon over 4. Okay, if 0 is less than absolute value of x minus, what was a? Negative 1, so that should be x minus negative 1 will give me a plus, x plus 1, it's less than delta. Then what I'm hoping is that the absolute value of f of x minus L is less than epsilon. So we're going to consider absolute value of f of x minus L. Remember, the limit in this question we think is 9. Okay, we want to consider this. Whoops, I should write consider this. Let's consider absolute value of f of x minus 9. All right, so let's write absolute value of f of x minus 9. And we're hoping that we can simplify this and eventually show that this is less than epsilon. Okay, so let's plug in what f of x equals. F of x is going to be negative 4x plus 5, the top piece of the piecewise function. Since that's coming from the fact that 0 is less than this absolute value, 0 is less than the absolute value of x plus 1, that meant x is not equal to negative 1. And that gives us the top piece of our piecewise function. F of x equals negative 4x plus 5. Okay, and now we're going to do a lot of the simplification steps that we did in the scratch work. Okay, we end up with absolute value of negative 4x minus 4. And with this, I can factor out a negative 4 and get absolute value of negative 4 times x plus 1. Now let's split this up into absolute value of negative 4 times absolute value of x plus 1. Absolute value of negative 4 is positive 4 times absolute value of x plus 1. Now I'm going to use the other part of what we're given. The absolute value of x plus 1 is less than delta. So this will be less than, let's keep the 4 as it is. And absolute value of x plus 1 is less than delta, so I can write delta like that. Let's write the reason. This is since, let's move this a little bit. Since, that's coming from the fact that since x plus 1 and absolute value is less than delta, that is for this step. And now we'll plug in what delta equals. So this equals 4 times delta. Delta is epsilon over 4, which equals epsilon. And that's what I wanted. Absolute value of 4x minus 9, we created this chain and eventually got it's less than epsilon. All right, and now I cleaned up this so it's a little bit easier to read. Overall, the proof should be easy for the reader to follow. So if you write the proof and you realize it's kind of messy, it's a good idea to rewrite it just so it looks clean. So what we just got, thus, the absolute value of f of x minus 9. We started with that, we simplified it, and eventually showed it was less than epsilon. Therefore, the limit is what we said it is. The limit as x approaches -1 of our function equals 9. And I'm going to use my symbol for end of proof, this square that's shaded in. And I want to end this video by noting that this was an example of an epsilon delta proof. And my function was linear. And I would say these ones are not bad. But epsilon delta proofs get much harder for non-linear functions. In our next class, we'll do an example with a quadratic function. And it'll be harder. So when we present that, be ready to slow down the video, rewatch certain parts, and even then, it is totally going to be normal and expected that you'll have questions, because it will be tough. But it'll absolutely be doable. It'll just take time to think through it at your own pace and practice it.